Hello everyone and welcome back to Math 110, Introduction to Number Theory. And in today's video what we're going to talk about are linear diophantine equations. Diophantine is referring to the Greek mathematician Diophantus of Alexandria, and Alexandria being the Egyptian city. And he existed somewhere around 200 to 300 CE. And no one really knows what Diophantus's age was when he died, but he did leave some mathematical problem whose solution suggested that he lived to at least 85. So Diophantus, just by the way, butchering the Greek would be a diophantos or something like that, but in English we say Diophantus. And what he studied were equations involving ratios and integers. So finding solutions to equations that are specifically whole numbers or ratios. The book that he's most famous for is called Arithmetica, and here's the title page of some Latin edition of it. And one interesting thing is he actually also came up with early algebraic notation. Before his contributions, everyone would just write out equations longhand, like the cube of the unknown minus twice the square of the unknown plus 10 times the unknown less 1 is 5, something like that, just completely written out. But it's great having polynomial notation these days. He didn't write it the way we now write it. Instead, it looks Greek to me. So this, just for the fun of it, there's kappa to the upsilon, which is x cubed, and alpha with a line over it means times 1. And then when you put different things next to each other, so this is zeta times iota with a bar, which was x times 10. And so putting them next to each other meant addition in his notation. And then he had this symbol which meant the difference between what came to the left and what comes to the right. And similarly, delta to the upsilon was x squared, beta with the bar was 2, m was the constant, so x to the 0 if you want, and then iota with an accent and a breath mark, I guess is, I don't know the Greek word for it, but presumably it's the word for equality. And then I guess epsilon bar, because it's the fifth letter of the alphabet, is 5. So, taking all the positive terms and the minus terms, we could write it in the Diophantine algebraic notation like so. So, in honor of Diophantus, Diophantine equations are integer polynomial equations with integer unknowns. So, over the next few slides, what I'm going to do is mention a couple of examples of Diophantine equations. So the first is one I like quite a lot, and they are the platonic solids. The platonic solids are polyhedra, which are three-dimensional figures, which are constructed of a bunch of faces and edges and vertices in 3 dimensions. So, for example, the cube, that is made out of 6 squares, 8 vertices, and 12 edges connecting them all. So the platonic solids are specific polyhedra which are regular. So that means every face is the same, so they're all regular n-gons, and around every vertex you have the same number of the polygons around them. So, so just setting up some equations. So if we have f faces and e edges and v vertices in our particular polyhedron, and if we're considering platonic solids, so each face is an n-gon, a regular n-gon, and each vertex is surrounded by mu faces. Mu coming from the I think Greek word monodromy, meaning to walk around. Then all 5 of these variables must solve a few equations. Well, one is an inequality, that they're all non-negative and that they're integers. And then there are these 3 equations. The first one, it's a nice result from topology, and it's that if you take the number of vertices minus the edges plus the number of faces, if you have a polyhedron that's sort of sphere-like, then it's 2, and that's called the Euler characteristic. Another equation is that if since each face has n edges, if you multiply the faces times n, then you get twice the number of edges, because each edge has two faces on either side of it, so that would be double counting it. And also, around every vertex, there are mu edges sticking out. And so mu times v, again, is double counting the number of edges, because each edge has two vertices on either side. Okay, so we got these three equations, 5 inequalities, and through some analysis, which we won't do, one can show that there are only 5 different solutions. And also, in Euclid's Elements, that original geometry textbook in book 8, he shows that all 5 of these are indeed constructible. So by this analysis involving linear diophantine equations, we figure out what the maximum set is, and then through some more work you can show that this is the set. So I think that's pretty cool. Another example that is very old are Pythagorean triples. So remember that the Pythagorean equation is an equation that relates the two side lengths of around the right angle of a right triangle to the hypotenuse. And the equation, of course, is a squared plus b squared equals c squared. But we could wonder about just integer solutions to this, so treating this as a diophantine equation. And a Pythagorean triple is a solution to this equation where not all 3 of these numbers are 0. Because 0, 0, 0 is a solution, it's just sort of uninteresting. So some examples, you probably know that 3 squared plus 4 squared is 5 squared, but also 6 squared plus 8 squared equals 10 squared, and so on and so forth. So one question is, I guess, how many solutions are there? Are these the only 4? Or maybe there's 15 more? Or maybe there's infinitely many. So can we find them all? This does end up having a full solution, which I'll go through just because I think it's a cool thing. But the main part of this lecture is going to be linear diophantine equations and not these quadratic ones. Okay, so here's a hint as to how. So if we divide both sides of the equation by c squared, then we can rewrite it as a rational squared plus some other rational squared equals 1. And recall, x squared plus y squared equals 1 is the equation of a circle in the plane, specifically a unit circle. So the problem of finding these Pythagorean triples reduces to the problem of finding points on the unit circle where both of the coordinates are rational. So points with rational coordinates is how they're referred to. So a really good observation about this problem is that if you did have a rational coordinate, then you could take the line through it and the point 1, 0. So that's 1, 0. And if you look at the slope of this line, the slope is rational. So on one hand, we know that whenever we have rational coordinates, then this line has a rational slope. So the question then is, well, does every rational slope give you a rational point? And so if we set up the system of equations where if m is the slope of this line, and so then y equals m times x minus 1 would then be the equation of this line. But then we also have the other equation, which is the equation of the unit circle. Then we can go through and solve it, and it turns out to have just rational functions for the two coordinates. So if we did substitute in some rational number for m, then x and y would both be rational numbers, and so it would be a rational coordinate. So rational slopes really do correspond exactly to all the rational points on the circle. Though there is one complication, which is that the point 1, 0, its line, I guess, would be the vertical line, and its slope is infinity. So really we want to do rationals along with infinity for this to actually be a correspondence, so one-to-one correspondence. Okay, another classic example of a diophantine equation is Fermat's last theorem, which I put in quotes because it's not like he really proved it. So the claim by Fermat was that if you had three natural numbers that are positive, and also some other natural number, and if these four numbers satisfy a to the n plus b to the n equals c to the n, then n must be 1 or 2. So we saw the n equals 2 case on the previous slide with Pythagorean triples, and the n equals 1 case is just a plus b equals c. So linear equations. Those are very, very easy to solve. So the surprising claim by him was that if n is 3 or bigger, then there are no solutions to this where all three numbers a, b, and c are positive. We need positivity because 0 to the n plus 0 to the n, equals 0 to the n. So the way that he, I guess, came to this theorem was he was reading his copy of Arithmetica by Diophantus, and I guess by thinking of related problems I saw in the book, then he just wrote in the margin around 1637 that he had a marvelous proof of this, but the margin was too narrow to contain it. So over the course of 350 more years, mathematicians tried to uncover what that proof that was too large to be in that margin, unfruitfully for a very long time, and which makes it seem apparent that maybe he really didn't know how to prove it. And so many mathematicians tried to prove this claim, and it was only in 1994 that a full proof actually did get written down by Andrew Wiles, building on a whole lot of other work and some very deep number theory. Okay, so those are two examples so far. A more applied example is integer linear programming, which it's a weird sort of like programming. Don't think about it as computer programming, but it's more of it comes originally from some military research where programming has to do with how do you move resources around. So anyway, integer linear programming is if you're given some linear constraints, which are some equalities or inequalities with integer coefficients. Everything's an integer in sight. And also a linear objective function, which is some function that's that produces an integer given all the variables involved. Then we want to maximize this objective function, subject to the constraints and only using integer solutions. So here's an example that I made up to illustrate this idea. So let's say that we are a stationery supply company, and we manufacture pencils and pens. And pencils, we know, take 3 units of labor to produce, and pens take 5 units of labor. And we know that we have 23 units of labor available, and we want to spend those units to produce pencils and pens. And suppose also that we know that pencils will give us 1 unit of profit and pens will give us 2 units of profit. The question is, can we maximize the profit somehow? So how many pencils and pens should we make to make the most amount of profit? So translating this into equations, let's say that x is the number of pencils and y is the number of pens. First of all, 3x plus 5y is the total amount of labor it takes to make x pencils and y pens. And we know that that has to be greater than or equal to 0 because there's no negative labor. And also has to be at most 23 because that's how much we have available. And also x and y both have to be non-negative because you can't make a negative pencil or pen. And our objective function is x plus 2y, which is the profit that we want that we would make given x pencils and y pens. Turns out integer linear programming is a very difficult problem. It ends up being NP complete, But at least for small examples like this, well, I actually didn't do it by hand. I just asked Mathematica to check it for me. But in principle, there's only finitely many points here, so we can go through and check. So, okay, what did I graph? So what I'm plotting is for each x and y, whether or not it's satisfying the constraints. So the horizontal line here is the 0 is less than or equal to x, or 0 is less than or equal to y constraint. So it has to be above the, or it has to not be below the x-axis. Then there's the 0 is less than or equal to x constraint, which is that a solution can't be to the left of the y-axis. And then this 3x plus 5y is less than or equal to 23 constraint. That's this diagonal line, and solutions have to be on it or below it. So I went ahead and plotted all the points for which this is possible. So this line only actually runs through 2 integer points. So anyway, if our problem were instead what are all the points on this line that satisfy the constraints, then those would be them, and I just did it exhaustively. Anyway, if we want to maximize x plus 2y, I guess it turns out that 1 pencil and 4 pens is optimal. If we were able to make fractional pens and pencils, then it ends up being that that's the point that would optimize everything. But that's 0 pencils and 4 and a little extra pens. So that is not something that we can produce. So what we'll tackle first for diophantine equations are linear diophantine equations. And specifically, we're going to deal with one equation, 2 unknowns, because this is like the simplest case that is not too difficult to see sort of what's going on. And it's also, it has complexities, which is good. So more precisely, what the question, what are all the integer solutions to ax plus by equals c? We want to describe the set of all x and y, where x and y are integers, such that ax plus by equals c. And just a notation warning, so we've been using pair notation for GCD, but we're also going to use it for points. So that's an unfortunate thing about the parenthesis notation for GCD. But in context, we'll figure out which one's which. Okay, so using our algebra 1 techniques of just subtracting by and dividing by a, supposing a is non-zero, that's not going to cut it because this is not necessarily giving us integers for x, right? Because like, I don't know, 1 minus 2y over 3, if y is 0, then this is 1/3. So that's not an integer. Also, things can be somewhat more complicated with the way that the GCD of a and b might be, as we will see. On our way to understanding this problem, let's recall a few facts to get started. So first of all, basic fact, by the definition of GCD, the GCD divides both of the numbers we're taking the GCD of. And in particular, by the linearity property, the GCD divides ax plus y for all x and y. So when we have ax plus by equals c, the GCD of a and b will always divide this left-hand side. So if S is the set of all ax plus by for all x and y, being integers, then the GCD of a and b divides every single element of S. Okay, fact 3 is that Bézi's identity implies that the GCD is in the set S. So we have that the GCD divides every element of S, and also that the GCD is in it. So another thing is that S, because every element is divisible by it, we can write it as the GCD times z for varying z, or in, I guess more simply, it's the set of all c that are integers, such that the GCD divides c. And through all this, we get a bunch of logical equivalences. So let's say that ax plus by equals c has a solution for these x's and y's. Then one thing is, because the GCD divides ax plus by, then c is an element of S. And also conversely, if c is an element of S, then this equation has a solution. And also, we characterized what S was in this previous line as that the GCD divides C. And so, ax plus by equals C having a solution is equivalent to the GCD of A and B dividing C. So summarizing so far, whenever we have A, B, and C integers, then the set of all solutions, the set of all integer solutions to ax plus by equals C is non-empty if and only if the GCD of A and B divides C. So that is a more exciting condition than you might be used to with the real numbers. So we're going to break this up into two cases. The homogeneous case, which is when C is 0, so solutions to ax plus by equals 0, just like what you might be familiar with in linear algebra. And then we're going to use the homogeneous case to help us solve the general case. So in this slide, we're going to suppose that A and B are both non-zero, because when both A and B are 0, this is easy to solve, because x and y can be just anything. If A is non-zero and B is 0, then y can be anything, but then x has to be 0. And similarly, if B is non-zero and A is 0. So the analysis is a lot more straightforward. Okay, so let's take a look. So we're assuming A and B are non-zero. And one thing we can do is take the A and B and divide by the GCDs. And that's, of course, because the GCD divides A and the GCD divides B. And implicitly here, I'm dividing by the GCD of A and B. For notational convenience, let's let A prime be this quotient and B prime be that quotient by the GCD. And let's fix that. That should be a B. Okay, so a fact is that the GCD of A prime and B prime is 1. And well, one reason is by dividing by all the common divisors, they have no common divisors anymore. Well, 1 is the common divisor. But I guess a rigorous reason is that if since the GCD divides both A prime and B prime, if anything that divides A prime also divides A. And in particular, it divides, so it divides A. So the GCD of A prime and B prime times the GCD of A and B will divide both A and B. And since that's a common divisor of both, and it's positive, that means it has to divide the GCD of A and B, and that implies that this has to be 1. And some terminology that I think we did not mention yet is that when the GCD of two numbers is 1, then they're called coprime. Okay, so to analyze this, let's suppose that we have a solution, and we'll try to put it into a form that then we can use to see what all solutions must look like. So let's suppose that x and y are solutions to a prime x plus b prime y equals 0. Then, so certainly a prime divides a prime x, and because b prime y is negative a prime x from this equation, then a prime must also divide a prime y. So now this is where coprimality comes in, and I'm leaving this lemma as an exercise, but it's also in the first section of the textbook. And that's if we have a pair of coprime integers, and the first integer divides the product of the second integer and some third integer, then the first integer must divide the third integer. And so this is somewhat similar to the primality property, but it's relative to this relationship for A prime and B prime specifically, that their GCD is 1. Okay, so with this lemma in hand, then what we can conclude from it is that a prime must divide y. And since that's true, by definition, there's some k, that's an integer, such that y equals ka prime. And so we can substitute that into our original equation that we're supposing. And so we have a prime x plus b prime ka prime is 0. Notice, though, that there's an a prime on both sides, or in each of the monomials. So we can cancel it out because a prime is non-zero, which I'll write that assumption right here. And since it's, okay, so then we have x plus b prime k is 0. And so solving for x is negative b prime k. And thus, we have the solution written in the form that x is negative b prime k and y is a prime k. And something that you can check, which I won't check right here, but I guess it's actually, well, we can just check it. If we take the set of all of these numbers, then these are all solutions. And that's, that's an easy check, which I'll just do quick. So a prime times minus b prime k plus b prime a prime k is negative a prime b prime k plus a prime b prime k. And that is 0, of course, because they cancel out. Okay, so just reiterating, assuming we had a solution, we can put it in this form, and also everything of this form is a solution. So this is the solution set for this homogeneous equation, assuming that both a and b are non-zero. So now that we've handled that case, let's summarize the whole thing. So, for the here's the lemma. So let's say that we have two integers a and b, and we let S be the solution set to ax plus by equals 0, where x and y are integers. Then, depending on which collection of a and b are 0, there are 4 cases. The first case is that both are 0, in which case every pair of integers is a solution. So in the second case, a is 0, b is non-zero, and you can check that it's all the pairs x is 0 for varying x. And then if a is 0, or non-zero but b is 0, then the solution set is all pairs 0y, where y is some integer. And then the fourth case is when they're both non-zero. And then this is just copied from the previous slide, but written in terms of a and b instead of a prime and b prime. So it's the set of all minus b over the GCD of ab times k, and a over the GCD of a and b times k for x and y. So there doesn't actually need to be 4 cases here. Cases 2 and 3 are actually encompassed in the third one. Everything does work out. It's just the proof we did, it assumed that a and b were non-zero for it to work. But I'll just put in parentheses just to remind ourselves that we don't need all 4 cases. And so this would be, let's see. So I can rewrite this as, so putting this in parentheses, this is just or a is not equal to 0 or b is not equal to 0. Okay, so we've solved the homogeneous equation. Now let's look at the general case, which is when c is allowed to be non-zero. And as we saw before, the GCD of a and b has to divide c for there to be a solution at all. So let's suppose that the GCD of a and b does divide c for this. So we handle this in 2 parts. 1, finding a particular solution, and then 2, finding a general solution from that. So the particular solution is just some integers x0 and y0 that solve the equation. And you can find this in any way that happens to work for you. There is a general method for this, and that is through the Euclidean algorithm, which I'll show you how. So here's one way to find it for this example. 6x plus 4y equals 8. So by the Euclidean algorithm, we calculate the GCD of 6 and 4. So the GCD of 6 and 4 is the GCD of 4 and 6 mod 4. And of course, 6 divided by 4 is remainder 2, but just writing that out, it's 6 equals 1 times 4 plus 2. That's the division algorithm. Okay, so 2 is the remainder, and so it's the GCD of 4 and 2. And so then we do the next step of the Euclidean algorithm, which is that's the GCD of 2 and 4 mod 2. And applying the division algorithm again, I got that 4 is 2 times 2 plus 0. And so 0 is the remainder. And the GCD of any number in 0 is that number. So the GCD is 2, as one would expect from 6 and 4. Just, I guess, from their prime factorizations. So now we apply the Euclidean algorithm in reverse, which means taking all the steps we did and then trying to find the coefficients for Béziers identity. So we know that 2 is 1 times 2 plus 1 times 0. That's just the first step for how we reverse this. It's always going to be 1 times the GCD plus 1 times 0. Then what we do is we remember that 0 was the remainder after division. So that's the 0, and that's this 0. And I'll link these up. So then we solve for the remainder. So 4 is 2 times 2. And we, 4 minus 2 times 2 is 0. So I substitute that in for 0. So that goes right there. So now we have that 1 times 2 plus 1 times 4 minus 2 times 2 is 2. Then the numbers that are showing up are, so this GCD is 4 and 2, so I want it to be something times 4 plus something times 2 is 2. So I take everything times 2 and everything times 4 and rearrange it. So let's see. So we had 1 times 2 minus 2 times 2, so minus 1 times 2, plus 1 times 4, plus 1 times 4, and so that's where we are right now. Then 2 is a remainder. So what we want to do is, okay, so linking those up, then solve for 2. So that's 6 minus 1 times 4, and substitute it in, and then do the similar thing of collecting all the 6's and collecting all the 4's. So we get minus 1 times 6, and then minus 1 times minus 1 times 4 plus 1 times 4. So that would be 2 times 4. Great. So minus 1 times 6 plus 2 times 4. So we found the two coefficients for Béziers identity for the GCD of 6 and 4. So that's what I mean by applying the Euclidean algorithm in reverse. So from this, we see that, well, 6 times minus 1 plus 2 times 4 is 2. And if 2 divides 8, which is good, otherwise there's no solution. And so multiplying by the quotient of 8 and 2, which is 4, we get 6 times minus 4 plus 2 times 16 is 8. And these two numbers show that we are solving this equation. So this is the particular solution that we found through this process, minus 4 and 16. Okay, so now we have the particular solution, and now we want to see how we create the general solution from that. And just like in linear algebra, if you happen to have a solution to one inhomogeneous equation and you subtract another solution, then you get a solution to the homogeneous equation, where the difference in the x's is the first x and the difference in the y's is the second y. So we know how to solve homogeneous equations. So like using our example, so let's say that we had a solution, 6x plus 4y equals 8, and then we subtract off this particular solution that we found. Then the equation we get, so this third equation, is 6 times x plus 4 plus 4 times y minus 16 is 8. No, that's not what I mean. I mean equals 0, of course. So using the formula from the previous slide, so that we're in the case of 6 and 4 being non-zero. So the first variable, 6x plus 4, then is the negative second coefficient divided by the GCD, so minus 4 over 2 times k. And then the second variable, which is y minus 16, is the first coefficient over the GCD times k, so 6 over 2 times k, where k is just some arbitrary integer. So then solving for x and y from this, we get that xy equals minus 2k minus 4, comma 3k plus 16 for k in the integers. Yeah, so that is the complete solution to this equation, 6x plus 4y equals 8. So that's the solutions, let's use green. So that's the solutions to 6x plus 4y equals 8. There's something about all that that feels a little ad hoc to me, something that only seems to work for these two variable, one equation systems. So I wanted to discuss another point of view. And what we're really sort of doing is that we're trying to find some good change of variables to make a simple equation. So what do I mean by that? So the thing that we're solving is that we have this 1 by 2 matrix AB, and we have this 1 by 1 matrix C, or I guess a column vector with one entry, C. And we're trying to solve for this column, this 2 by 1 column vector, that AB times XY equals C. So like in linear algebra, usually finding some good basis change usually makes everything clear for how you solve something. So what ends up being what we're doing is that we're trying to find a 2 by 2 invertible matrix P with integer entries. These are known as unimodular matrices. And we want this matrix P to have the property that if we take our 1 by 2 matrix and multiply it by P, then we get a 1 by 2 matrix where the second entry is 0. So there's some integer d in the first entry, then 0 in the second. And if we do manage to find such a matrix P, then if we consider a change of variables where x prime and y prime are related to x and y by multiplying by this matrix P inverse in this way, then what we can see is that solutions to the original equation that we're looking at are equivalently solutions to this equation where we slip in this identity matrix. So that didn't change anything at all. It's actually literally the same. Well, not literally, but because they're written differently, but it is equal on the left sides. But we get this equation. And then by replacing, well, AB times P with the fact that we know it's D0 and P inverse XY with these new variables x prime and y prime, then we get this new equation, which is a lot easier to solve. Because, well, let's just write it out in a non-matrix form. This is dx prime equals c. And, well, that's it. That's the one equation. So y prime is free to be anything, but x prime is just a solution to this division problem. So, for example, if after we find this matrix P, we see that D is non-zero, and let's also say that C is non-zero, then there are solutions if D divides C, and in particular, x prime must be C divided by D, and y prime is free. So, now that we've solved for x prime and y prime, since it's related to x and y through this P matrix, then x and y equals P times the x prime y prime vector, which we solve for, which is P times C over D y prime. And by varying y prime, we get the complete set of all solutions. So it's probably better to see how this works in practice. And on the left, we'll do it using just changes of variables. And then on the right, we'll see how this relates to matrices. So, okay, so we have 6x plus 4y equals 8, the equation from the example before. And I'm just going to do a couple variable substitutions that I know will work based on, well, I've already written it out, and also based on knowing what we're wanting to have happen. Because it does take a little bit of guessing, at least if you don't know the algorithm. Okay, so so here's sort of the algorithm. We want to keep replacing one variable with some sum of two other variables to try to keep, reducing the numbers to the remainder after division. Like we're wanting to do the Euclidean algorithm, but looking in this completely different form. So, so 6 is the larger number, so I want to do 6 mod 4 to get the remainder. And how do I do 6 mod 4? Well, I want to do 6 minus, in this case, just 4. That will give us the remainder. So to implement that, I had x is x prime and y is minus x prime plus y prime. These are the new variables. And when we substitute these in, what ends up happening is that, well, we still have 4y prime, but then the 6x prime minus 4x prime ends up doing the subtraction. So 2 is the remainder of 6 by 4 after division. Similarly, so 4, I want to reduce that mod 2. And so I chose this change of variables. So x prime is x double prime, this new variable, minus 2y double prime, and y prime is y double prime. And after the substitution, then, well, the minus 2y double prime that we substitute in here ends up subtracting a 4y double prime, which cancels out the 4y double prime. Okay, so we're left with this equation, 2x double prime equals 8, and there are infinitely many solutions to it, but all of them require that x double prime equal 4. Now reversing this process, we see that x prime is x double prime minus 2y double prime, and I substitute them in to get 4 minus 2y double prime, and y prime is y double prime. Then undoing the next substitution, x is x prime, which is, again, 4 minus 2y double prime. But then y is minus x prime plus y prime, so it's minus 4 plus 2y double prime plus y double prime, which is minus 4 plus 3y double prime, and then that gives us the solution set. So by having y double prime vary over all the integers, these pairs of numbers give us all the solutions, which is exactly what we got before by the other method. Sorry, I actually don't mean exactly the same. We got some different coefficients, or we got a different particular solution, basically. This one was minus 4, 16, and then the one that we got here was 4 minus 4. It doesn't matter which particular solution we chose. So let's reiterate this process using matrices, which are a wonderful invention because we only record all the coefficients and we don't have to keep writing all the variables, which makes things sort of hard to follow. What we have here is we have these A matrices. I'm going to just call them all A on each step. I guess it could just be like A1, A2, and A3. And then we also have these P matrices, where at each step, A equals 6, 4 times P. So that's what we're trying to have happen. And we're trying to find the right P matrix so that 6, 4 times P is in the form something 0. So again, following sort of the Euclidean algorithm, we have 6 and 4, so we want to subtract 4 from 6. So let's take column 1 minus column 2, put it into column 1. So we get 2, 4. And then we want to reduce 4 mod 2. So we take column 2 minus 2 of column 1, put that back into column 2, and that's 2, 0. And it turns out that we can just apply all of these same column operations to the identity matrix in the same order, and then that will give us the appropriate P matrix. So let's see. So I start with the identity matrix, and I subtract 1 of the second column from the first. That gives us the minus 1 down there. And then we subtract 2 of the first column from the second, and then that gives us a minus 2 up here in the upper right entry, and then 1 minus negative 2 gives us 3. And we can indeed check that 1 minus 2 minus 1, 3 times 6, 4 is equal to, so 1 times 6 minus 1 times 4 is 2, and minus 2 times 6 is minus 12, plus 3 times 4 is 12, so that's 0. Great. So that worked out. Okay, so then the next step is we take this reduced matrix and we want to solve this equation, which I'm using double primes just to match up with the left-hand side. And this equation is just 2 times x double prime plus 0 equals 8, just written out not in matrix notation. So x double prime is 4, and y double prime is free to be any integer. And then, using what was on the previous slide, then the xy solution can be written as p times the solutions that we found for this reduced version of the matrix, which is this product, and then multiplying it out, we get the exact same solution from this change of variable process. Just done in this more principled way, maybe. So I want to point out that the process that we did with matrices is very similar to that process for finding inverse matrices. So we can use that, which recall, if you want to find the inverse of a matrix, you can row reduce the matrix where you've augmented it with the identity matrix. So instead of augmenting it horizontally, we can augment it vertically and do column operations. And that's a way to not have to then go back and modify this identity matrix after everything. So, okay, so let's say we want to solve ax plus by equals c. Then what we can do is start with this 3 by 2 matrix, AB, with the identity below it, and then apply column operations to column reduce it to some number 0 and then some matrix P down below. And we need to be careful about which column operations we're allowed to apply. And so first of all, permutations are perfectly valid because there are, well, you can undo permutations by unpermuting. The other is when we scale, we can only scale by units. Because, for example, if we multiply by a column by 2, we can't then unmultiply it by 2 by multiplying by something else, because that would be multiplying by 1/2, which is not an integer. And we want to make sure that we've got this integer matrix that's invertible as an integer matrix. So then there's also adding a multiple of a column to another, which is just like adding a row of a matrix to another. So really the only thing that's different is that we're only allowed to scale by units. And once we've gone through this procedure, then it turns out, as one can check, that the 1 by 2 matrix AB times this P matrix that we get down below is D times 0. And also that P is an invertible integer matrix, which I was a little sloppy earlier when I said this, but I mean with an integer inverse. So I mean, where it's a matrix where every entry is an integer after inverting. So, right. If we then have this equation, d0 with x prime y prime equals c, and we find, and this is a solution, and let's say that we have a solution x prime y prime, then we can multiply that solution by this P matrix to get a solution to the original equation. So this is a procedure by which you can solve all of these equations. Assuming you get the hang of doing these column operations to put it into this form. One nifty thing is that this d here is actually, if you make it positive, but like by scaling this column by -1 if necessary, then that is actually the GCD of A and B. And the reason for this is that, if we do the Euclidean algorithm for A and B, then each step along the way, we can turn it into a different column operation. So the first step, of course, is permuting the columns, because just to write that out. So the Euclidean algorithm is that AB's GCD is B A mod B. And also remember that this is B, A minus the floor division A mod B times B. So here's the idea. Step 1, permute the two columns. In step 2, do A mod B by taking column 2 and then subtracting some multiple of column 1. So we keep applying, I guess, just the first and the third operations to carry out the Euclidean algorithm. And then in the end, we're going to get the GCD in the first entry and 0 in the second. So this is why we are able to reduce it, and also why that entry will be the GCD. Now that we've talked about these one equation, two unknown linear diophantine equations, I thought let's talk about the general case. I won't give you a procedure for how to actually solve them all the time, because it's somewhat more involved, but at least in principle, everything is just the same, just more rows, more columns. So, okay, so we're going to look at linear diophantine systems of equations. So linear systems of equations where all the coefficients are integers and all the variables are integers that we're solving for. So here's the problem statement. So let's say that we have an m by n matrix with integer entries, and let's say that we have an integer vector in Zm. And we want to figure out what is the solution set to ax equals b, where x is also an integer vector. And so what our example problem of these 1 by 2 matrices shows is that row operations are not enough to be able to solve these, and we have to do something somewhat more sophisticated. And the solution is that we have to allow column operations. And also we need to remember, record the column operations that we did so that we can sort of undo them in the end, which is what that P matrix is all about. Okay, so here's the procedure. We make this block matrix where we have the augmented matrix in the first two blocks, and then the identity matrix down here. And these zeros, they don't actually matter. It's just to fill it out. And then what we want to do is apply row operations of the type that don't scale by anything but units for the first blocks, so for the first rows, because we just don't want to do any row operations to in down here, or I mean this part. And then also for the first column of blocks, we want to apply column operations so that in the end we get a matrix of this form where D is diagonal. Where diagonal for a non-square matrix means that it's 0 everywhere except along wherever that diagonal might be. It might get truncated off one side, so that's okay. So the theorem that we're not going to prove in this course is that by applying row and column operations like this, we can actually get it into diagonal form. And also we can get it into a normal form called Smith normal form. And in the end, what it will look like is all the diagonal entries are non-negative, and they're non-negative natural numbers, and each one divides the next. So for example, it could be 2, 4, 4, 0 down the diagonal. So for this, say, I guess it's a 4 by 5 matrix. That would be a Smith normal form. Yeah, so that can always be done, and it's this. It's basically Gaussian elimination, but you're also at the same time doing the Euclidean algorithm to clear things out by doing column operations. And this ends up being a very important theorem for algebra. Okay, so that was abstract. Let's just do it concretely. And so let's say that we have the system 2x1 minus 6x2 minus 4x3 is minus 2, and 2x1 plus 2x3 is 4. So suppose we don't really need this more advanced technique for this equation, because we can eliminate one of the variables right off the bat pretty easily. But let's just see how it would work. Okay, so I've written it in matrix form, and then I put the A matrix in the upper left corner, the identity matrix in the lower left, and then the B vector in the upper right. I just leave these three entries blank because they really don't matter what they are. Okay, so I'm going to do row operations first. So I'm going to take the second row minus the first to clear out this 2. And okay, so in normal Gaussian elimination, we would want to divide the first row by 2 to get a pivot entry, but we're not allowed to divide by 2. We're only allowed to multiply by plus or minus 1. But luckily we can cancel it out here anyway. So that's what I did. You can check the arithmetic. Then what I did was I realized I could cancel out the minus 4 and the 6 by subtracting the first and second columns to do so. I'm not really following any algorithm here. It's just something I saw. So column 3 minus column 1 minus column 2, stick that into column 3. So 2 column operations of the third type. And that ends up clearing those out, but then this affects the I matrix down below, or the P matrix. So we get a minus 1 in those 2 entries. The next thing is we can clear out this minus 6 by subtracting the second row from the first. So that clears that out, and it also modifies this B vector. And now we've got it in this matrix in Smith normal form, because it's diagonal, and also each entry is positive and each divides the next. So now that we've gotten in this form, we have this equation, just like before, where we want to solve it using this D matrix and this new B prime vector. And if we write out what it's saying, it's that 2x prime 1 equals 4, and 6x prime 2 equals 6. And so x1 prime has to be 2, and x2 prime is 1, and x3 prime is allowed to be anything. I gotta fix that. That was a little mistake. Okay, so now that we've solved for that, what we do is we take the solution vector for this, so 2, 1, x3 prime, and multiply it by the P matrix that we got, and then that gives us all of the solutions. So this is a parametric solution to this linear diophantine system of equations. Yeah, so that is that. And so let's summarize everything. What we saw was what are diophantine equations. Those are like polynomial equations where everything is an integer. And a linear diophantine equation is a diophantine equation that's linear, no more than that. And we also saw linear diophantine systems in the end. We saw how to solve ax plus by equals c over the integers. And where over the integers means where everything in sight is an integer. And we also saw, at least partly, how to solve the more general problem of linear diophantine systems, ax equals by, over the integers. And it's only partly because I didn't show you an algorithm for how to put things into Smith normal form. I just asserted to you that this was the case. But it does end up being some combination of the Euclidean algorithm and Gaussian elimination. So anyway, I hope you found this to be interesting, and I'll see you next time.